Today we're talking about 1.3 transformations of function graphs. The first thing to write down are kind of a definition of what parameters are. Parameters are certain numbers introduced to a function can transform the graph of a function in a number of ways, including a translation or shift of the graph, and that could happen vertically or horizontally. You could also stretch or compress the graph, again, vertically or horizontally, or you could reflect the graph, again, vertically or horizontally. If you are catching this video at home outside of class, please pause the video here so you have some time to write this down. All right, now that you've got this written down about parameters, let's take a look at some different types of transformations. Given an original function, we're going to call it f of x. The following are transformations that you could do to that function. So f of x, we have to first define what that is. So I might say f of x equals 3x squared plus x minus 2. Okay, and once you've defined what f of x is, then you can start changing it up and moving it around the graph in these different ways. The first type of transformation is called a translation. And really what a translation is just shifting the graph around. You're going to shift it up, down, left, and right. And this is very similar to what you've done in geometry. The only difference is in geometry, you got a shape. Maybe you got a square or a triangle, or you got something that you put on the graph, and then you did a translation where you shifted that shape up, down, left, right. You maybe dilated it, so you made it bigger or smaller, things like that. Today, we're going to look at what if it wasn't just some, defined shape, but what if it was maybe a function that even went from negative infinity to positive infinity, had a domain of all real numbers. How would we do something like that? Well, as long as you've got f of x defined in some way, you know what that is, then you can translate it by shifting it up or down by adding or subtracting some constant value, so that's just a number, at the very end. Now, I want to be really clear that when you're shifting up, down, when you're making any changes that are vertical, any changes that are vertical are going to happen outside of the function f. So what I mean by that is notice that it says f of x, and then at the end of it, you're going to put plus k. If you put plus 3 at the end there, everything about that function is going to shift upwards 3 units. If you put minus 2, everything about that function is going to shift downwards 2 units. And that's kind of intuitive. Vertical changes are intuitive. They make sense to us. It's how we would think, it's how we think that they would do. So someone in chat says, does the letter you use matter? Not necessarily. Some books will say like a C here, or some books will say a D. I've used H and K for these letters for purposes that are going to show up later on. So later on in this unit, later on in this course, we're going to use H and K again in these exact spots. So that's why I've used these letters. But in terms of like what letters you use, not really, because these are just placeholders for numbers, if that makes sense. All right, so I was talking about how vertical changes are intuitive, like they kind of make sense to us. If I add 5 at the very end, it makes sense that it goes up 5. If I subtract 7 at the very end, it makes sense that this goes down 7, right? That makes sense to us. But what doesn't make sense, or I guess what I should say is what's not as intuitive, what's not what we would think it would do, is shifting left and right. Note here that now for these two, I am adding or subtracting some number h, but I'm doing it on the inside. Horizontal changes, okay, horizontal changes happen on the inside of the function. So on the inside of these parentheses, I've got f of now x plus h, or f of x minus h. And to me, when I look at x plus h, I know that x is kind of, I'm looking left and right as part of the domain, right? X is left and right, x is the domain. I would think that when I see x plus 5, when I see x plus 5, my brain goes, well, everything should move to the right 5 because that's a positive 5. Or when I see x minus 9, I would think that everything gets shifted over to the left 9 because that would make sense to me. But horizontal changes are, as I said, not quite as intuitive as vertical changes. In fact, this is the opposite of the way that your brain wants it to be. When you see plus 5, you want it to go to the right 5, but you're actually shifting to the left 5. When you see minus 10, you want it to go to the left 10, but it doesn't work that way. It actually goes to the right 10. So vertical changes, again, happen on the outside of the function, and those are intuitive to us. Horizontal changes happen on the inside, okay, inside the parentheses, x plus h, x minus h, and those are kind of the opposite of the way that I would want them to kind of be. And later on, we're going to see actual examples of this, and you're going to be playing around with this stuff. So if you're not quite sure what all this is meaning yet, that's okay. We're going to be playing around with it in just a moment. So do me a favor, in chat, let me know if you are done writing this down and you're ready to go to the next page here. Just type done in chat. All right, I'm seeing a bunch of people say done. Give it a little bit longer for those that are still catching up. What's up?
Mr. Weird things, I can see your cursor moving, but I can't see the screen.
Yeah, I'm not sure what's going on with your connection to Zoom, but that's strange.
Zoom doesn't like me today.
Yeah, at least you've got the notes to look up on a separate tab in Schoology. So, all right, I'm seeing most people say done. If you haven't quite finished there yet, and you didn't type to me that you're not done yet, don't worry. All of this is available on Schoology. Okay, so let's look at another type of transformation. This is called a dilation. Okay, a dilation, this is stretching and compressing the function. Now, what's another time that you've seen or heard the word dilation or dilate? By the way, write these down, please, if you haven't started already. What's another time that you've heard or maybe seen or used the word dilate or dilation before? There's a common one that maybe people kind of forget about. Anyone have an idea? So someone types your eyes. Luke typed your eyes. Yeah. So when you go to the eye doctor, sometimes they put these drops in your eyes that dilate your eyes, or really what they're doing is they're dilating your pupils. They're making your pupils enlarged so that it's easier for you to, easier for them, I should say, to see and work on your eyes. And that's exactly what's happening. The lens, or your aperture, if you kind of think of like a photography, that's widening, it's letting more light in, which is also why they give you these special glasses when you leave the eye doctor. Okay, they don't want you to hurt your eyes by having too much light come into your eyes. So that's exactly what's happening. We are making it bigger. We're making the function bigger, or we're making it smaller in some way. So let's look at the different ways that we can do that. The first is going to be vertical changes. And again, vertical changes happen on the outside of the function. So we've got f of x, it's intact, and then at the very front, I've got a times f of x. So some number times f of x. Well, if that number is a whole number, an integer a, it's going to stretch the function vertically. And I want you to think about when you do take something and you stretch it. When you pull on it up and down, the parts that are to the left and the parts that are to the right usually stay about where they're at. But the stuff in the middle, from the top to the bottom, those get stretched upward and downward. And that's exactly what happens when we stretch a function vertically. So if I multiply by a 2, a whole 2, the function is going to get stretched to double the length, okay, double the distance. If I do 3 times f of x, it's going to triple. If I do 4 times, it's going to quadruple. 5 times, it's going to be 5 times the length, upwards and downwards. But if I do a fraction, let's say 1 over a, so 1/2, it's going to compress or shrink the function down to half the size. If I do 1/3, it's going to further compress it or shrink it down to 1/3 of the size. If I do 1/10, it'll be really, really small, go down to 1/10 of the size. Okay, and that makes sense to us. If at the very beginning I multiply by 3, I would expect it to triple in length. It's 3 times the size. If I multiply by 1/2, that makes sense. I would expect it to go down to half of the height. But what doesn't make sense, again, are the horizontal ones. Okay, horizontal changes, 2 things. Horizontal changes always happen on the inside, and they're kind of the opposite of what I would think that would happen. So for example, f of b times x, f of b times x, I'm multiplying x by some number, let's say 2. In my mind, I would think that if I multiply the x by 2, I'm stretching it horizontally by 2. But that's not what's happening. I'm actually compressing it to 1/2 of the size. If I multiply by 3, I would think that I'm stretching it horizontally, left and right, to 3 times the width. But that's not what's happening. I'm actually compressing it to 1/3 of the width. Now, if I multiply by a fraction, though, f of, let's say, 1/2 times x, I would normally think this brings it to half the width, but now, because it's a horizontal change, it's going to stretch it to whatever, okay, if it's 1 over b, it's going to stretch it to whatever b is. So if it's 1 over 2, it's going to stretch it to double the length, 2 times. If it's 1 over 3, it stretches it to 3 times the length. 1 over 4, 4 times the length, and so forth. And the last thing are going to be reflections. I'm going to see if I can get both of them on the same page here. Okay, reflections are just like what you would think when you look in the mirror. Okay, it's a mirror image of what the function originally looked like. And there's 2 ways that we can reflect. We can reflect vertically and we can reflect horizontally. Remember, vertical changes, 1, always happen on the outside. So that negative, you'll see, that negative happens on the outside. That's negative f of x. And what that's going to do is it's going to reflect the function vertically. So this part gets a little confusing for students sometimes. When we reflect vertically, we're going to look at the x-axis, which is odd because the x-axis is left to right. It's one of those flat horizontal lines. But the reason that we look at the x-axis is because anything that was on top is going to get flipped down to the bottom, and anything that was on the bottom is going to get flipped up to the top. So that's what I mean by vertical, a vertical reflection, is top goes to bottom, bottom goes to top. And we look at the x-axis, and that's kind of what our mirror is. To reflect horizontally, remember anything that happens horizontally is going to be on the inside. So I'm going to have f of negative x in those parentheses now. And that's going to reflect horizontally, again, kind of weird because the mirror, okay, is going to be the y-axis now, which is odd because we're reflecting horizontally, but this is a vertical line. And anything to the left of that vertical line is going to get flipped over to the right side, and anything to the right is going to get flipped over to the left side. Okay? So these are the different transformations that we're going to be working with for our various functions. We're going to be shifting the function around, up, down, left, right. Those are called translations. We're going to be stretching and compressing functions, both vertically and horizontally. Those are called dilations. And lastly, we've got these reflections where, like a mirror image, we're going to be flipping things from left to right to left, or bottom to top to bottom. But one thing I definitely want you to remember, okay, I'm going to scroll down a little bit here. One thing that I definitely want you to remember is right here. All vertical changes happen outside of the function, these outside of the parentheses. And all horizontal changes happen on the inside of the function, that's inside the parentheses. And that vertical changes are more intuitive to us. They're what I would think would happen. And horizontal changes are just about the opposite of what I think would happen. Okay, so this takes us to lunch. So we're going to pause here. I'm going to leave this up on screen, and you can finish writing that if you haven't written that already. We're going to go to lunch, and when we come back, we're going to have an activity. Okay?
Mr. Eng,
All right, now that we're back from break, we are going to head over to Desmos, which is a calculator and graphing utility. Okay, thank you, Mr. S, for posting that link in chat. So if you're in class, go ahead and click on that link in chat so that you can get to this page. If you are catching this video outside of class, it is Desmos, desmos.com/calculator. I'm sure if you just Google Desmos, it'll probably be the first link. Okay, so go ahead and do that now. If you're in class and you need to exit the full screen, you hit escape on your keyboard and then you can open up a new tab. All right, now that you're here, let's make this graph a little bit more user-friendly for what we're going to be doing. So I want you to navigate over and find this wrench up in the top right corner, graph settings, and you're going to click that. And then I want you to turn off minor grid lines, so uncheck minor grid lines. And then for the x-axis and y-axis, notice that these are going by 2, and I would rather have them go by 1s. So for the step, I'm going to click on each of these step lines, and I'm going to click 1. Just type 1 there for both. And now I can click off of the settings, and I've got this graph, which I can move around and such, and it is everywhere going by grid lines of 1, which is really nice for what we're going to be doing. The next thing I want you to do, and if you recall, I'm going to go over to the notes again. If you recall, I originally had said that we have to first define what our function is, right? We have to define what f of x is before we can do any of these transformations. So what I want you to do is I'm going to move these notes aside. I want you to have your notes out in front of you. So maybe put them in front of your Chromebook or your computer. And I'm going to move them over to my other screen. And I want you to type in here for this first line, some equation. I want you to define what your original function f is going to be. So you could do something like f of x equals, okay. Someone says, how are we setting this up again? So go to the graph settings here, uncheck minor grid lines, and then type a 1 for each of these steps. And it should look like this. Okay, so that's how to set up the graph. And then now I want you to define what your function is going to be. We have to pick something for f. So you could do something like, I don't know, x squared minus 3 if you wanted. You could do something as simple as just like a regular line, so like 4x plus 2. Okay, or if you want to get a little fancier, you can do that. If you don't know the shortcuts on your keyboard for how to do like exponents and such, there is a utility that you can use here, show keypad, and then now you can do like x to the third, so x, and then I would hit a to the b thing here again. Okay. And that would go, I can hit that, and I can do 3 here, and then just hit the right arrow on your keyboard or the right arrow on this keypad to bring you down to the regular line again. All right, so from here, just create whatever function you want. Here I'm going to do, since I already got x to the third here, let's do x to the third minus 2x plus 1. That is how I'm going to define my original function f. So go ahead, set up whatever function you want to use. All right, now that you've got that, notice that you're going to have some points that are kind of highlighted for you. You've got like a point here that hits the x-axis, maybe some things here. I want you, if you can, I want you to find a point where it kind of snaps into place along the grid. So for example, all of these have decimals, but this one is a nice 0, 1. That's a nice 0, 1. And if yours doesn't have one that snaps into place like that, maybe just try changing your graph around a little bit. Maybe try changing like this 2 to a 3 and seeing what happens. I notice now if I change this to a 3, I've got multiple points that snap in place. So maybe I'll use this one instead. All right, now what we're going to do is, using the notes that you have in front of you, we're going to kind of play around with our function. So we're going to try different types of transformations. The first thing I want to try are translations. So let's do some vertical translations. In the notes I see, if I have f of x, and notice just typing f of x there, this blue curve, this blue graph overlaps the red one because they're exactly the same. Why? Because I've already defined what f of x is. F of x equals x to the third minus 3x plus 1. It is that, okay, it's going to be this function. So now when I go f of x and then maybe plus 2, I can see that the blue one has now taken that red graph and it has shifted everything up 2 units. And how I can confirm that is by looking at those snapped points. So for example, this is negative 1, 3. By moving this up 2, but not left or right any, the x should stay the same, negative 1, but the y, 3, should go up 2, which it has, negative 1, 5. I can also see that this point down here, which was 1, negative 1, going up 2 is going to be now 1, 1. I can do the same thing for moving it downwards too. So let's click off of this, have all those points disappear on us. And if I do f of x minus 4, I can see that the blue curve is now shifted downwards from where the red one was. So this point, negative 1, 3, is now at 1, negative 1. Good. Now, those ones made sense to us because those are vertical changes, right? That makes sense to us. But now I want you to also play around with the horizontal translation, so the horizontal shifts. Again, if I do x plus 3 here, my brain wants this to go to the right 3. But when I type it, I see, oh no, this actually moved the red over to the left 3 units. Okay, now it's a little overlapping here. If you want to have it completely off of one another, you could type in a different number and see what happens. So now I've got plus 4 here, and everything shifted to the left 4 units. Okay, so this point, which was at negative 1, 3, if I shift this to the left 4 units, that means that the y value, 3, is going to stay the same, but the x value is going to go, Okay, that way left 4 more to -5, which it has. Same thing with like points like this. So this is 1, -1. The y value is going to stay the same at -1, but the x is going to go from 1 to -3. I can also do the same thing by, instead of plus some number, I can do maybe -5. Okay, and if I do -5, notice everything gets shifted now to the right 5 units. So this -1,3 is now at 4,3. So those are the different translations we can do. Let's talk about some of the other transformations. Let's do some dilations. So some stretching and some compressing. Let's start with the vertical ones because, again, those are a little more intuitive to us. They make a little bit more sense. Now, starting with f of x again, if I put some number at the front to multiply f of x, let's say a 2, I see that from the red to the blue, everything got stretched to double the length, right? This one, which was at -1,3, is now at -1,6. So the y values doubled. Same thing here. This y value was -1. So at 1, -1, this is now 1, -2. But take a look at the points on the actual x-axis. Those zeros didn't change at all, which means that when I pulled this vertically, the left and the right parts, okay, those stayed the same. It's just everything in the middle got stretched upwards and downwards. I could do the same thing for compression. So if I do, instead of 2, let's say multiply by 1/2. If I multiply by 1/2, we'll see that again, these zeros didn't change. So left and right, those stayed where they were, but now this, which was at -1,3, this is now -1,5, which is half of where it used to be. If I do 1/3, that point, which was -1,3, is now at -1,1 because it is 1/3 the height. And again, those vertical changes, those make sense to us, right? If I multiplied this by, some large number, let's say, I don't know, 4 or something, we can see, again, it's still just stretching up and down. I can move my graph around. It's still just stretching up and down, but left to right, it's staying put. Now the horizontal stretching and compression, again, horizontal changes happen on the inside, so we're going to go to the inside of the parentheses, and they're always kind of the opposite of what I would think they would be. So when I do 2 times x, I would think I'm going to take this and I'm going to stretch it. I'm going to stretch it to double the width. This thing is going to be twice as wide. But it actually shrinks or compresses it to half of the width. And notice that these are the same heights, right? The y value, this maximum here, is going to be the same height, and this minimum here is going to be the same height, I guess height the other way, so a shallow point. But the x's and the y's just kind of shrunk in. They got compressed, as if we took it and we squeezed it. Right? If I do a 3, this will be 1/3. Okay, it'll shrink down to 1/3 of what it was before. 4, 1/4, and so forth. Now, let's see what happens when I do a fraction. So 1/2. I would think that this would be the one that squeezes it to half the size, but it actually doubles. Okay, it extends it to twice as wide. If I do 1/3, it stretches it out to 1/3 of the width. If I do 1/4, it'll stretch it to 1/4 of the width. But notice that the maximums and the minimums are going to remain the same height because I didn't do anything Okay, it's like you take dough and you stretch it this way. You didn't do anything to the top or the bottom of that dough, so it's going to stay the same height. You're just stretching it out. And then finally, my reflections. Okay, if I do a negative at the very front, this is going to create a reflection vertically. So anything that was above the graph, so this part here, this hill here, is going to get reflected below, as you see here. And this little tiny valley is going to get shifted or reflected above. Same thing with these tails. Okay, this tail which was going upwards is now going to go down. This one which was going down, which is now going up. So that's a vertical reflection, and it's reflecting about the x-axis. Someone asked, are we expected to remember all of these different functions? They're going to come up from time to time, and I'm always going to remind you of these different things. So they may not be things that you have to necessarily memorize at this point in time. Okay, if I put a negative in front of the x, this is going to create a horizontal reflection. So if you look at the y-axis, anything to the left is going to get reflected over to the right. Anything from the right is going to get reflected over to the left, which you see here. And actually creates kind of a cool image. So this, which is on the left side, is going to get shifted over to the right like this, how my mouse is moving. And then this will get shifted over to the left side or reflected over to the left side to create this image. So for the remainder of today's class, I would like you to just play around with the different types of transformations, because I have found that learning about it from a book or just writing graphs or drawing graphs down on paper is one thing, but being able to actually see what's happening as you type it and be able to change things in real time is so much better for learning this material. And you can do multiple things at once. So for example, if I want to shift this up 2, I'd put a +2 there. But if I also wanted to shift it maybe left or right, I could do x, -4. So now it's being shifted to the right 4 and up 2. And I could also do a vertical reflection on top of all of that, where now it gets shifted up, it gets shifted to the right, and then it's reflected. Okay, so for the remainder of the time, just toy around with this, and if you have questions, please reach out to either myself or Mr. Seegers. Again, if you're catching this at home, I'm gonna stop the video here, but hopefully you take some time to just play around with Desmos, and remember that you have to identify first what f of x is before you can do any of these transformations.